All right, so not only do you have to solve exponential equations, you have to also solve some log equations. Those can be found. 36 and 37 are going to be very close to the ones on the test. And 37. In the test review, the packet that has like 40 some odd practice questions. The first one, 36, has, let's see, let me get my sketch pad up. Question 36 says that we have log base 3 of x minus 5 plus log base 3 of x plus 3 equals 2. All right, the first thing we want to do is if we can create one log out of this one. Let's see here. Sorry, you guys, I'm still getting used to this new platform. Let me pull my sketch pad back up. So if we can make just one log of it, like we say the log base 3, since we're adding them, we're going to multiply them together. Don't forget, if I'm going to multiply x minus 5 times x plus 3, all right, you have to do it like this, or you can just FOIL in your head. So I'm just going to do it in my head. So I'm going to get x squared. Let's say it's going to be minus 5x plus 3x, which should be minus 2x and then minus 15. And that's going to be equal to 2. Now I know that 3 to the power of 2 is going to be equal to that. So we have 3 squared, which, do I really need to write 3 squared? Can I just write 9 is equal to x squared minus 2x minus 15. And this is a quadratic, so I need to solve it like a quadratic, which means subtracting 9 from each side and setting it equal to 0. I can only subtract 9 from another number, so I'm going to subtract 9 from that 15, and it's going to be negative 24. The easiest thing would be if I could factor this. So let me think. Are there two numbers that add up to be negative 2 and multiply together to be negative 24? I want to say negative 6 and positive 4. Negative 6 and positive 4, so x minus 6 and x plus 4 equals 0. So I'm going to get two answers here, but hopefully you've realized from web work that, sorry, Arnold's being goofy. Hopefully you realize from web work that you need to make sure it can work in the original problem first. So my x sub 1 is positive 6, x sub 2 is negative 4. We've solved that quadratic. Will both of these work in the actual equation up there? Because remember, these cannot be 0. And I think the only one that's going to work here is going to be, or less than 0, I should say, 0 or less than 0, is going to be the positive 6 is going to be the only one that's going to work for both of those, because negative 4 in both instances is going to give me a negative number. So my answer for this one is 6. You can always, always, always check yourself. Using the calculator, you can graph these and see where they are going to intersect. In this case, what you might want to do is, well, the way I always do it is I graph both sides of the equation. So you can put this into like y1 and you would put 2 and y2. Maybe, let me see if I can figure out, I'm going to pause, see if I can figure out how to do it in Desmos, because this computer doesn't have the TI software that I can show you with the graphing calculator, and maybe I can show you what it looks like. So I'm going to just close this for a second and see if I can graph that for you guys. All right, so you can in Desmos graph these equations. You can do it in the TI2, which is all you're going to be able to use on the test, but you can graph these functions in Desmos by going to function, and then I clicked on the log base A, and it lets you type in whatever base you want. So like you can see where they cross, x is equal to 6, and that was one of the answers we got. The other answer was extraneous, and that was x equals -4, I believe. Let me check. Sorry, you guys probably already have this answer in front of you. And x equals -4. Okay, and obviously that's not even in the domain, so there's no answer over here. So you can always check by graphing it which one is correct, or you could just graph it to find the answer if you want anyway. It really doesn't matter to me if you just want to explain in the test how you did it. So then let's try another one. Let's try another one here, which is log of 3x, so just a regular log base 10. Log of 3x minus log of x minus 1 equals log of 4. Now if they have the same, oops, that looks like a base 4. I'm going to do this. As long as they have the same base on both sides, you can go ahead and set them equal to each other. The problem is we need to turn this into one log first. So since it's subtraction, it's going to be log of 3x over x minus 1 is equal to log of 4. And now we can just say we're going to solve this 4. I'm going to turn this into a fraction. 4 over 1 is equal to 3x over x minus 1. I'm going to cross multiply, so I get 3x is equal to 4x minus 4. Don't forget, I have to multiply this 4 by this x and this -1. Don't forget to distribute there. Okay. Then subtract 4x's from both sides, and you get -x is equal to -4, or conversely, +x is equal to +4 here. And if I put it back into the original function, I don't have any extraneous values for that one. Let's see, we can graph it to check. And so when I graph both sides of that equation, you can see right here that my answer was x is equal to 4. That is where the two sides of the equation intersect. All right, a half-life problem. And this is the exact problem from the test. I just took out the numbers so we can make up some numbers. Say we put the half-life of silicon-32 is, and it is pretty high, so how about I just make it 676 years. If blank grams is present now, how about we just say 46 grams is present now? How much will be present in, and how about we say 252 years? Round your answer to 3 decimals. So what we need to do here, you guys, is because it is continuously decomposing, we need to go back up, and luckily on your test it'll have this one right here with the a sub 0 e to the kt is what we need to solve. So we're going to put it in. Let's see if I can just do it here. Oh, I better go back to the sketch pad. It's so much easier to use. So 676, 46, 52. I may have to go back and forth for a minute here. So we know that what we are going to have is a sub 0 e, and we know it's decomposing, so I'm going to say negative k t. And it tells me that the half-life, or we decided that the half-life was going to be 676 years. So that's what we're going to put in for t when we are first solving this, was 676 years. And the amount we start with is going to be here, which was 200. Oh, that's what I'm forgetting, is that number, which is oh, no, just 46 grams present. 252 is the other one. So 46 grams present. That's what we're going to change this to be. Now, here's the kicker. Our half-life means that it's going to take that 676 years. There will be half of the amount that we have. So we'll put 23 here. We'll have 23 grams after 676 years. So since we know that point, we can put those numbers in to solve for K. So what we'll do is we'll make this K times 676. Okay, so now we just have to solve for K, and then we'll have an equation that we can go back in and put, we want to know how much is going to be left after 252 years. So first we're just going to divide both sides by 46 now. The cool thing here is that obviously that's going to be half here, so you could skip that first part if you want. I always do it because it makes more sense to me. E to the negative K times 676. Now, because I'm using base E, I'm going to take the natural log of both sides. So I'm going to have the natural log of 1/2, or I'm just going to put 0.5, is equal to the natural log of E to the negative K times 676. Now, the cool thing about taking the natural log of E is that's just going to cancel. So I'm going to have the natural log of 0.5 is equal to negative K times 676, or why don't we just write it like this? Negative 676 K, and then divide both sides to get K by itself by negative 676. And that should give us our rate of decay. Our rate of decay. I need a calculator here. I'll pause while I get that out. All right, you guys, so if you put that into the calculator, the natural log of 0.5 divided by negative 676, you are going to get 0.00102537 on and on and on. Or look, Wolfram already did the percent for us, 0.0125%, 0.00103. How about we just do that, 0.00103. So K is equal to 0.00103. Now we can go put it back into the equation to figure out how much is going to be left after 252 years. So we say we want to know this A, how much is left. If we start off with 46, e to the negative 0.00103 times 252. And I'm just going to put that back into Wolfram Alpha. If I can remember those numbers, I'm going to write it down really quick. 46e, the negative 0.00103 times 252. Okay. I love Wolfram Alpha, especially because it will give you a bunch of different representations that you couldn't get on any normal like graphing calculators and stuff. So let's say 46 times e to the power, where's my caret, to the power of negative 0.00103 times 676. And let's actually put all of that in parentheses to make sure it all gets up into the caret. So it's giving me that answer. Let's see if that's what it is. Assuming E is a mathematical constant, yes it is, then our result is 22.9281 grams is going to be left over after 252 years. Okay. All right, and you can practice these questions as many times as you want by just making up as many different numbers as you wish. I'm going to stop this video here.